You sit down at a terminal and you're given access to literally the most powerful, expensive, and sophisticated machine ever built by human hands.
Right.
And I mean, you've read the headlines. This artificial intelligence is supposed to write production-level software architecture while you sleep.
Yeah, or coordinate swarms of autonomous agents to solve, like, global supply chain crises.
Exactly. It's allegedly on the cusp of discovering new pharmaceutical drugs, unraveling the fundamental laws of physics.
Mm.
You basically have all of human knowledge compressed into this massive neural network.
It's a staggering amount of compute.
Right. So you type in a prompt, and you don't ask it to cure a disease. You don't ask it to design a rocket engine.
Yeah.
You ask it to perform a task that a kindergartner manages with a simple song. You ask it for the alphabet. And the machine, this trillion-dollar culmination of human engineering, just completely falls apart.
It really is a stunning juxtaposition. We've normalized this idea that these frontier models possess superhuman capabilities.
Oh, absolutely. We treat them like magic.
Yeah, and that's largely because they can produce incredibly fluent, complex text that mimics deep expertise. But when you strip away that surface-level mimicry and test the actual foundational bedrock of their understanding, you expose this massive structural void.
And that structural void is exactly what we're focusing on today. We have a huge stack of source material in front of us, centered around this really fascinating report titled The Hassabis-Einstein Test for Operating Alphabets.
It's such a brilliant framing for the problem.
It really is. So our mission for this deep dive is to explore this profound blind spot in the absolute heavyweights of the AI world. We're looking at OpenAI's GPT-5.6 Sol, Anthropic's Claude Fable 5, SpaceXAI's Grok 4.5, and Google's Gemini 3.
I mean, these are the models that define the current boundary of artificial intelligence.
Yeah.
They are literally the systems driving the global economy right now.
And we're going to tear into what their failure to recognize a simple linguistic alphabet actually reveals about the future of artificial general intelligence, or AGI.
Right.
More importantly, we're going to explore what this means for our very definition of intelligence itself.
Because that definition is fundamentally shifting right now.
It is. So my promise to you, the listener, is that by the time we finish this deep dive, the way you look at a simple string of text on your screen or the underlying mechanics of your favorite chatbot is going to fundamentally change.
Yeah, you definitely won't see magic anymore.
Nope, you will see the architecture.
Yeah.
And all of its flaws.
Right. And to understand why an AI failing an alphabet test is such a catastrophic problem for AGI, we really have to start with the philosophical framework of this report.
Let's unpack that, because there's a fierce debate right now about what constitutes actual reasoning, right?
Exactly. There's this tension between true reasoning versus what is simply highly advanced memory. If we're trying to build a system that can push humanity forward in AGI, it cannot just function as an incredibly sophisticated search engine.
It can't just be humanity's tape recorder.
Precisely. It needs the capacity to look at raw, completely unstructured evidence and recover the hidden structure beneath it.
And the report frames this through that brilliant thought experiment called the Hassabis-Einstein Test. Let's really map out what this means for everyone listening, because it's not just a clever name.
Yeah, go ahead.
Think about the state of physics. Right before Albert Einstein finalized the theory of general relativity back in 1915, scientists had this massive pile of raw data, right?
Decades and centuries of it.
Exactly. They had astronomical observations. They knew about the anomalous precession of Mercury's orbit, this weird wobble that completely defied traditional Newtonian physics.
Because the data was absolutely there, but the underlying structure explaining it was completely missing.
Right. And that is the crux of the test. The premise asks, could a sufficiently advanced machine arrive at the mathematics of general relativity using only the raw astronomical data and mathematical tools available before Einstein actually published his theory?
The constraint is the whole point of the exercise.
Exactly. You cannot feed the AI Einstein's completed equations and then ask it to explain gravity.
If you do that, the AI is just demonstrating recall. It's literally just looking up a file in its massive database of human text and regurgitating it.
It's essentially an open book test where the student just copies the glossary. That proves nothing about intelligence.
Right. The machine has to look at the messy universe, the partial observations, and reconstruct the hidden theory entirely on its own.
Which isolates a really critical distinction in AI research right now. The gulf between declared knowledge and discovered structure.
That distinction is everything.
I want to make sure the mechanics of that are crystal clear. When you say declared knowledge, you're talking about information that humanity has already done the hard work of identifying, formalizing, writing down, and digitizing, right?
Yes, exactly. It's explicit.
It's the stuff blasted across Wikipedia, academic journals, GitHub repositories.
Declared knowledge is neatly packaged. Discovered structure, on the other hand, requires inferring the complete correct answer from raw evidence before anyone hands you the final puzzle.
It's the difference between statistical prediction and logical deduction. Think about it like this. Declared knowledge is like going to IKEA.
Oh, I love this analogy.
Right. You buy a bookshelf, you open the box, and there's a beautifully printed step-by-step instruction manual.
And every piece of wood is labeled with a little sticker.
Yeah, the screws are in a neat little plastic bag. The finished picture is right there on the cover. Building that shelf requires competence, obviously, but doesn't require invention.
You're just following a pre-existing path.
Exactly. Now, discovered structure is being dropped in the middle of a forest with an axe, a pile of raw, splintered wood, and a blurry black and white photograph of a chair.
And you just have to figure it out.
You have to invent the concept of carpentry, joinery, and load-bearing angles entirely from scratch.
That analogy captures the mechanical difference perfectly. Following the manual is essentially what large language models do today. They just trace the probabilistic paths that humans have already laid down. But inventing carpentry requires foundational reasoning. Now, if discovering the hidden laws of physics from raw planetary data is the ultimate test of this reasoning, the Einstein test, we run into a massive logistical problem.
Which is that we can't easily measure that capability today.
Exactly. We can't sit around waiting for an AI to invent a new branch of quantum mechanics just to verify if it has reached AGI. It's not practical.
We need a testable, bounded sandbox, a way to run this Einstein test in miniature with absolute precision.
And according to the source material, the perfect sandbox is language.
Specifically, the foundational, indivisible units of language, the alphabet.
Right. And at first glance, using an alphabet to test superhuman intelligence sounds kind of trivial, doesn't it?
Honestly, yeah, it feels incredibly basic.
We're socially conditioned to view alphabets as elementary because humanity spent centuries doing the grueling work of standardizing them, and now we just drill them into toddlers using blocks and songs.
It's literally the very first thing you learn in school.
Exactly. It feels basic to us because the cognitive load of discovery has been completely removed by our education system. But structurally, an alphabet is anything but trivial.
It's the finite, closed set of units from which an entire written universe is constructed.
Yes. It is the absolute operating infrastructure beneath everything. Spelling, dictionaries, keyboards, search algorithms, digital text encoding.
It's a closed mathematical system with exact, unforgiving boundaries. Take the standard English alphabet, for instance.
Right, there are exactly 26 letters.
Exactly. There aren't 25, there aren't 27. It's a rigid, closed inventory. And that rigidity is what makes it the perfect grading rubric for a machine.
There's no room for subjective interpretation.
Zero. We don't need a panel of human judges sitting around a table debating whether the AI's output feels linguistically creative or sounds plausible. You either identify all the units of the system flawlessly, or you fail the test.
However, if we want to use the alphabet to test an AI's ability to discover hidden structure, we immediately run into a massive experimental roadblock.
Oh, yeah.
Yeah.
This is where the methodology gets really fascinating.
We cannot use the English alphabet to run this test.
No, because the English alphabet is utterly contaminated in the AI's training data. I mean, the sequence A through Z is absolutely everywhere on the internet.
Think about the sheer volume of English language structural data fed into a model like GPT-5.6 or Claude.
It's incomprehensible.
They have digested millions of children's books, educational transcripts, ASCII code tables, dictionary prefaces, formatting guides.
And programming languages where A through Z are explicitly defined as string constraints.
Exactly. The completed, finalized list of those 26 letters is plastered across billions of pages of their training material.
So if you prompt a frontier model to output the complete set of units used to construct written English, and it perfectly spits out A through Z, you have absolutely no way of knowing what cognitive process just occurred.
Right. Did the neural network actually analyze billions of English words, separate the alphabetic characters from the numeric digits, exclude all the punctuation marks?
Filter out the emojis.
Yeah, filter out emojis, and dynamically infer the foundational rule that there are exactly 26 letters.
Or did it just statistically predict the next token in a sequence it has literally seen 10 million times? We just can't know.
Yeah.
The answer key has contaminated the experiment.
It's exactly like asking a student to solve a complex geometric proof on a final exam, but the completed proof has been written on the whiteboard at the front of the classroom for the entire semester.
You can't test their ability to deduce the formula if they can just look up and read it off the board.
Exactly. So the researchers behind the L26 benchmark had to find a completely different environment.
They needed a linguistic space where the AI has encountered massive amounts of raw evidence, the raw wood from our forest analogy, but where nobody ever published the IKEA manual,
And their brilliant solution was to use Bantu languages.
which creates the live, real-world Hassabis-Einstein experiment at the core of this report. Let's talk about why Bantu languages are the perfect testing ground.
It really comes down to how these massive AI models interact with global data. Frontier models essentially scrape the entirety of the digital world.
Right. And over the years, they have ingested an enormous amount of Bantu language text. We're talking about languages like Kinyarwanda, Bemba, and Luval.
And we should clarify, these are not small, isolated dialects. They are major languages spoken by millions of people across Central and Southern Africa.
So the AI has processed translated scriptures, expansive dictionary entries, vast databases of personal names, Wikipedia articles, local news websites, everyday social media text in these languages.
The models have seen the outputs. They have seen millions upon millions of words generated by these linguistic systems.
But historically, for many of these languages, the absolute foundational inventory, the definitive list of every valid building block, was never actually published on the internet as a single, closed, machine-readable standard.
The noisy, raw data exists out there in the wild in massive quantities. But the finished operating alphabet, the definitive answer key, simply didn't exist in a way that an AI data scraper could find and memorize.
So the models have been swimming in the language, but they were never explicitly handed the schematic.
This isolates the exact variable we're trying to test. Can a model examine everything it has absorbed about a language, all the chaotic, noisy, uncalibrated real-world text, and actually deduce the complete set of primitive units from which that language is built?
Can it separate the pure structural signal from the noise of the internet? Can it locate the exact invisible boundaries of a complex system without a human explicitly telling it where those boundaries are?
Because what the AI is looking for in a Bantu language isn't just letters in the way we think of A, B, and C.
Right, it requires mapping an entirely different foundational architecture.
Yeah.
The report uses the term operating alphabet. And I think we need to define the mechanics of that term because it shifts drastically depending on the language family.
The concept of an operating alphabet is so crucial here. The English language operates on single, isolated letters. But human language does not universally conform to the Latin alphabet structure.
If we force every language into a letter-by-letter paradigm, we're basically imposing an artificial, often colonial, framework onto systems that function entirely differently.
Exactly. Let's use Mandarin as an example to illustrate this. The foundational pronunciation system for Mandarin isn't a list of single, isolated letters.
Right. The operating architecture is based on a bounded inventory of legal pinyin syllables.
You can measure Mandarin's foundation through base syllables, which is a specific closed set, or you can measure it by attaching tones to those base syllables, which dramatically expands the inventory of valid units.
But the defining characteristic isn't the size, it's the fact that there is a finite, standard, structurally coherent set of units.
Yes, and for Bantu languages, the natural foundational unit is the syllable itself.
Typically structured as a consonant followed by a vowel, or a consonant cluster followed by a vowel.
Right, so a learner of Bemba or Kinyarwanda isn't conceptualizing the foundation as an isolated B and an isolated A.
The foundational indivisible block is ba or b or bai. These aren't just random letters smashed together. They are the literal atomic level of the language.
Yes, the L26 benchmark uses operating alphabet as a sort of universal umbrella term.
It represents the complete foundational inventory through which any given language fundamentally operates. So for English, the operating alphabet is 26 letters. For Mandarin, it's the standardized pinyin inventory.
And for Bantu languages, this operating alphabet is formally defined as the full syllable inventory, or the FSI.
I really want to dissect this FSI
Right.
because the report gets heavily into the structural mechanics here. A full syllable inventory isn't just a brute force spreadsheet, right?
No, not at all.
It's not where an AI just logs every single string of characters it happens to find separated by spaces in a text file. The researchers apply a very specific calibrated formula.
They define the FSI as the NSI union ASI.
Let's break down those variables for the listener. NSI stands for the Native Syllable Inventory.
Right, and this contains the pure historical, linguistically endogenous syllable structure of the language itself.
It is the architectural core.
Exactly. And ASI stands for the Augmented Syllable Inventory. This contains all the additional non-native syllables that have been integrated into the written language over time to support concepts from the outside world.
We're talking about things like borrowed vocabulary, foreign personal names, modern scientific and technological terminology, international geographic locations.
Right. When a new concept enters a culture, say, the word computer, the language often absorbs the word, and sometimes that word contains syllable structures that don't historically exist in the native system.
And the ASI explicitly tracks those structural augmentations.
Exactly.
Now, let me play devil's advocate for a second. If I'm an engineer trying to build a text processing engine, why can't the AI just rely on frequency?
What do you mean?
Like, if the word computer or the name John appears 10,000 times across a massive scrape of Bemba news articles, shouldn't the neural network just logically assume that the syllables making up those words are now officially native to the language?
Ah, I see.
If a syllable is used constantly in everyday text, why do we force the AI to perform this complex structural separation between native and augmented?
That is a great question, and it comes down to the fundamental difference between statistical frequency and structural lineage.
Okay, unpack that.
The data sets these frontier models are trained on these massive scrapes of the open internet. They're notoriously aggressively messy.
Right, think about the reality of a web scrape. You are not downloading pristine, peer-reviewed linguistic texts.
No, you are downloading a chaotic soup of human interaction.
You're getting typos, broken formatting, optical character recognition errors from scanned PDFs.
You're getting all of that noise. You're also getting historical colonial-era spelling inconsistencies that were never fully standardized.
Oh, wow.
You are getting rampant code switching, where a user might type half a sentence in Kinyarwanda and seamlessly switch to French or English for the second half.
So if an AI simply counts the frequency of character strings and concludes, well, this syllable appeared 500 times in my dataset, therefore it is a native building block of this language, it's going to construct a deeply warped foundation.
Mathematically invalid, yes. A typo that goes viral doesn't rewrite the historical grammar of a language.
That makes perfect sense. A foreign name appearing frequently in a news corpus does not retroactively alter the phonological rules of the native system.
Precisely. A true artificial intelligence, a system grounded in structural reasoning rather than mere statistical parrot matching, must possess the capability to distinguish between those layers.
It has to tell the difference between a core native structure, a valid supported augmentation like a loanword, and outright digital noise.
It must infer what actually belongs to the core system.
It's basically the difference between looking at a bowl of soup, analyzing the chemical composition, and understanding the recipe.
Versus just dumping everything you found on the kitchen counter into a pot and calling it a coherent dish.
Exactly. So we've established the target. The AI models need to independently discover this pristine, structurally calibrated, full syllable inventory.
Right.
But we are dealing with entirely different languages that have wildly different structural scales. How do you actually grade this?
That is the challenge.
How do you compare an AI's performance on a 26-letter English alphabet to its performance on a Mandarin pinyin system to a Kinyarwanda syllable inventory?
That measurement challenge is solved by the specific architecture of the L26 benchmark. It functions as a universal ruler for foundational mastery.
Which is so clever.
It is. The benchmark evaluates models across English, Mandarin testing both base and toned, pinyin Kinyarwanda, Bemba, and Luvelle.
And the sheer disparity in the sizes of these operating alphabets is just staggering. To give you, the listener, a sense of scale, the English operating alphabet has exactly 26 units.
The Mandarin-based pinyin inventory has 412 units.
And when you factor in tones, the Mandarin-toned pinyin inventory explodes to 1,642 units.
Massive.
In the Bantu language tracks, Kinyarwanda requires the AI to discover 490 syllables. Bemba requires 480. Luvali requires 245.
We are dealing with huge variances in the absolute number of foundational blocks.
Right, so if a researcher simply reports the raw output, if they say, oh, GPT-5.6 successfully recovered 312 out of 480 syllables for Bemba, but it also hallucinated 50 invalid structures.
It's incredibly difficult for an engineer, let alone the general public, to intuitively grasp the magnitude of that failure.
It's just noise. You lose the context of how broken the foundation actually is.
To solve this, the L26 benchmark takes all of those wildly divergent inventory sizes and mathematically scales every single result onto a universal 26-point scale.
Which makes so much sense. The 26 in the benchmark's name doesn't imply that every language literally has 26 letters. It is a psychological translation tool designed for human comprehension.
Exactly, because you intuitively understand the English alphabet.
Right, if I tell you a $1 trillion model scored a 20 on the L26 scale, you don't need a PhD in linguistics to know what that means. You instantly recognize that the AI is effectively missing 6 letters of the alphabet.
If it scores a 13, it only knows half the foundation.
It forces the abstract technical failure into a very concrete frame of reference.
But the calculation behind that final number out of 26 is what makes the benchmark so incredibly rigorous. The researchers didn't design this to hand out partial credit for effort.
No, the final score is dictated by a strict mathematical formula. L26 equals 26 multiplied by recall multiplied by precision.
Let's delve into the mechanics of that formula because it is the linchpin of the entire test. You are multiplying the theoretical maximum of 26 by 2 strict percentage metrics, recall and precision.
You have to penalize the model for both omissions and inventions.
Yes. Recall evaluates the model's comprehensiveness. Out of the true, verified, complete inventory of syllables that actually exist in the language, what percentage did the AI successfully discover and output?
So if the language has 400 native syllables, and the AI only outputs 200 of them, its recall is exactly 50%.
And then precision evaluates the model's accuracy and structural restraint. Out of all the syllables the AI decided to output in its final answer, what percentage were actually real, valid linguistic units versus hallucinated garbage?
This precision variable is critical.
Oh, absolutely, because it neutralizes the most obvious way a machine learning model might try to cheat the test.
Right, without a severe penalty for poor precision, an AI could theoretically succeed through just uncontrolled enumeration.
It could just generate a script that vomits out every mathematically possible combination of consonants and vowels, knowing that the actual valid syllables are buried somewhere in that massive data dump.
Right, if you guess every conceivable sound a human mouth can make, you will technically hit all the real ones. But that isn't mastery.
No, that's just an algorithmic shotgun blast.
Exactly. An operating alphabet is defined by its exactness. It is a closed inventory.
If a model pads its response with fake, non-existent units, its precision score crashes, dragging the entire final L26 score down with it.
And conversely, if it exercises restraint but forgets real foundational units, its recall score drops, and it still fails.
The standard has to be binary.
Yeah. If an AI generates A through Y perfectly, but omits Z, it does not know the English alphabet. A score of 25 out of 26 is a fundamental failure of mastery.
It has to be this strict because downstream technological infrastructure requires absolute stability.
You cannot build a functional spell checker, a reliable digital dictionary, a predictive keyboard, or an accurate text-to-speech engine on an operating alphabet that is constantly shifting.
Or forgetting rules or hallucinating new letters based on statistical whims. The foundation must be fixed. The L26 sets that ruler.
And crucially, this test is administered blind. The AI models are placed in the sandbox, given the prompt to output the complete foundational inventory of the language, and given absolutely zero hints.
No manuals, no external context.
Nothing. They only have the raw, massive corpus of training data compressed within their neural weights. So how did the brightest, most advanced minds in the artificial intelligence sector perform when subjected to this strict, blind measurement?
The results from the July 2026 leaderboard are, quite frankly, staggering.
They really are.
They reveal a massive chasm between what we assume these models know and what they actually comprehend.
Let's establish the baselines first. For the English operating alphabet, the average score across the major models is 26.0.
Absolute flawless mastery.
Right. For Mandarin pinyin, specifically the toned inventory, the average is 22.6. That is an incredibly strong performance, demonstrating really robust structural recall.
But then the data hits a cliff, and it is not a gradual sloping decline as the languages become less represented in the training data.
It is honestly an absolute vertical drop. On the Kinyarwanda track, the average score plummets to 10.4 out of 26.
On the Louvale track, it drops to 6.1.
And on the Bemba track, the average score across the most sophisticated AI systems on the planet is a 5.1 out of 26.
To truly comprehend the severity of that collapse, we need to analyze the performance of the individual heavyweights, because the aggregated averages actually mask some of the most spectacular failures.
Let's start with OpenAI's GPT-5.6 Sol. This is a model routinely heralded as the frontier of complex reasoning.
Right, it's designed to navigate highly complex, multi-step logical tasks.
But when subjected to the blind Bemba operating alphabet test, GPT-5.6 Sol scored a 3.1.
A 3.1 out of 26.
Translate that into the English alphabet equivalent. That is a model being asked to provide the foundational units of a language, confidently giving you A, B, and C, and then utterly failing the rest of the assessment.
It either completely forgets the remaining 23 letters, or it starts hallucinating numbers and Cyrillic characters to fill the void.
It is a total collapse of mastery.
And we have to be very careful to clarify what that 3.1 actually signifies. It does not mean that GPT 5.6 only possesses 3 words of Bemba vocabulary.
Oh no, the model is highly articulate. It can translate complex sentences between English and Bemba.
It can engage in a fluent, culturally contextual conversation in the language. It exhibits a very convincing surface-level fluency.
It can talk the talk.
It can generate plausible tokens in sequence. But beneath that surface fluency, it lacks foundational mastery.
It is constructing a massive, elaborate house, but the foundation is built on quicksand.
It's predicting the shape of the roof without actually knowing how many bricks are in the walls.
Now let's look at the next contender, SpaceXAI's Grok 4.5.
Yeah.
Across the Bantu language tracks, Grok achieved an average score of 8.7 out of 26.
So mathematically, it outperformed GPT 5.6 Sol.
Moving from roughly 3 equivalent letters to roughly 9 equivalent letters is technically an improvement.
It is a higher number, but structurally it is still a massive failure.
Right. A system that only knows 9 letters of the alphabet does not possess a functional alphabet.
The objective of the Hassabis-Einstein Test isn't to fail slightly less disastrously than the competing model. The objective is to evaluate whether the AI can successfully recover the complete bounded generative system.
And an 8.7 demonstrates that Grok 4.5 is entirely incapable of doing so.
Completely incapable.
Then we have Anthropic's Claude Fable 5. Now, the data here requires a much deeper analysis because Claude Fable 5 registered a 14.7 average on the Bantu tracks.
But as the report extensively details, you cannot look at that 14.7 as a simple reflection of its discovery capabilities.
Right. There is a profound behavioral quirk baked into the architecture of Claude Fable 5, and particularly its predecessor, Opus 4.8.
Yes. When researchers prompted the Claude models to blindly output the complete bulk inventories for these non-English languages, the model's API safety layer frequently intervened.
It blocked the attempt before the generative process even began. The AI actively refused to take the test.
Claude Opus 4.8 would intercept the prompt, decline the task, and explicitly articulate its reasoning.
It would inform the researchers that attempting to generate a complete, structurally flawless foundational list purely from its internal memory weights would inevitably introduce significant errors, omissions, and hallucinations.
The neural network essentially performed a self-assessment, realized it didn't have the explicit manual, and decided, I'm going to fail this test, so I am not going to guess.
Wait, it literally just refuses. That is a highly significant architectural trait.
In the field of machine learning, this behavior is known as calibrated uncertainty.
Calibrated uncertainty.
Right. It is the result of extensive reinforcement learning from human feedback, or RLHF. It represents a massive developmental leap over earlier generations of large language models.
Because older models would routinely, confidently hallucinate a completely fabricated alphabet, present it as undeniable fact, and basically gaslight the user.
Exactly. Recognizing the limits of your own knowledge is objectively a safer, more advanced behavior for a deployed technology.
You don't want an AI hallucinating medical protocols or legal precedents, so training it to refuse when uncertain is good engineering.
It is excellent safety engineering. But the report highlights a critical philosophical distinction here.
Which is that calibrated uncertainty does not equate to mastery.
It doesn't.
It's like a student walking into the final exam, reading the first question, walking up to the teacher's desk, and saying, "Look, I am deeply aware that I do not know the material required to answer this, and to attempt it would be intellectually dishonest."
The teacher might commend the student for their profound self-awareness and honesty.
But the student still gets a 0 on the exam. They do not know the material.
Exactly. The AI can feel the structural gaps in its own digital floorboards. It knows the infrastructure is missing.
But it entirely lacks the generative reasoning capability required to actually deduce and construct the missing pieces from the raw data it possesses.
Right. And as illuminating as these individual model failures are, there is a broader trend buried in the L26 benchmark data that is even more disruptive.
Yeah, it directly contradicts the fundamental driving assumption of the entire artificial intelligence industry. We need to talk about the scaling paradox.
This is perhaps the most counterintuitive finding in the entire report, and it challenges the core developmental philosophy of the major AI labs.
For the past decade, the tech industry has operated on this relentless mantra: bigger is inherently better.
The assumption is that if you exponentially increase the number of parameters in a neural network
Flood it with exponentially more compute power.
and train it on exponentially larger data sets, the model will linearly become smarter and more capable across all domains.
But the L26 benchmark data completely shatters that assumption. Let's look at the direct comparison between OpenAI's older GPT-5.5 model and their massive, cutting-edge, wildly expensive GPT-5.6 Sol model.
The baseline expectation is that the newer scaled-up model should completely crush the older iteration.
But on the blind Bantu average, the older GPT-5.5 scored an 11.8 out of 26.
And the newly deployed GPT 5.6 Sol scored a 6.7.
The capability actually degraded as the model scaled.
Yes.
How does that happen? Did the engineers accidentally break the multi-billion-dollar architecture? How does a model that is demonstrably vastly superior at writing Python code, orchestrating autonomous agent workflows, maintaining massive context windows,
Suddenly become significantly worse at identifying the foundational syllables of a language it is perfectly fluent in?
It's crazy.
Well, it doesn't mean GPT 5.6 is universally less intelligent. It means we fundamentally misunderstand what scaling actually achieves.
This performance drop perfectly isolates the mechanics of the scaling paradox.
When you dramatically increase a model's parameters and compute, you are essentially amplifying and reorganizing the statistical signals within its training data.
You're making it vastly more efficient at recognizing complex, probabilistic patterns.
Right. But if the foundational answer, the exact calibrated closed list of syllables, was never explicitly formalized and written down in that training data in the first place,
Scale cannot magically conjure it out of thin air.
increasing the parameters of a neural network does not grant it the magical ability to read a document that humanity never wrote.
It's akin to examining a deeply flawed, incomplete map with a more powerful magnifying glass.
That's a great way to put it.
The magnifying glass allows you to see the existing ink with incredible high-definition clarity. But no matter how powerful the lens, it will never spontaneously dry in the missing roads.
This entirely dismantles the default tech industry reflex to every complex AI problem. Whenever a model fails at a reasoning task, the immediate reflexive response from the engineering teams is, we just need to feed it more data.
Let's throw another petabyte of text at the training run. It's the ultimate tech bro answer.
And for this specific category of structural discovery, injecting more unstructured data is a complete fallacy.
We have to differentiate between a corpus and an operating alphabet.
Right. A corpus, a massive data set of web pages, articles, and books, contains millions of unstructured examples of a language being used in practice.
Whereas an operating alphabet is the explicit declared set of foundational rules that govern those examples.
Exactly. If I dump 10 million additional sentences of conversational Bemba into an LMM's training run, the model will undoubtedly become better at predicting the next plausible word in a Bemba sentence.
Its conversational fluency will improve.
But those 10 million scattered sentences will never collectively pause and explicitly inform the neural network. Attention. There are precisely 480 valid native syllables in this linguistic system.
Here is the exact boundary of the foundation.
Yeah.
And any structural deviation you encounter is a borrowed loanword.
Observing millions of examples of a system in action does not automatically generate a declared mathematical standard of the system.
The model must possess the internal architecture to actively execute structural discovery.
And the catastrophic L26 benchmark scores prove definitively that frontier-scale pattern matching, regardless of the compute power behind it, does not automatically bridge the gap to actual structural reasoning.
Listening to this analysis paints an incredibly bleak picture. It really forces you to wonder if these trillion-dollar architectures are just fundamentally, inherently incapable of processing the foundations of these languages.
Is there a hard, impassable limit to what neural networks can achieve?
Right. To answer that, the researchers executed a second phase of the experiment, and the data from the second phase flips the entire narrative on its head.
Everything we have discussed so far pertain to the blind condition of the test.
The models were thrown into the sandbox, handed the task, and denied any external assistance or structural context.
But the researchers didn't stop there. They introduced a second, contrasting test known as the scaffolded condition.
The mechanics of the scaffolded condition are really straightforward. This time, the models are not instructed to guess, infer, or discover the foundation.
No, the researchers explicitly hand the AI the fully calibrated full syllable inventory, the finalized FSI, directly within the prompt or the model's immediate context window.
It is the absolute equivalent of taking the complete perfect alphabet chart with every letter and corresponding sound clearly defined and taping it directly to the wall in front of the AI before the exam begins.
The prompt essentially says, here's the exact, verified boundary of the system. Now utilize it to complete the task.
And when you provide that explicit digital infrastructure, the performance metrics transform completely.
Let's look at the scaffolded scores.
Under this condition, Anthropic's Claude Opus 4.8 executed 15 out of 15 test runs with absolute perfect mastery.
SpaceXAI's Grok 4.5 executed 15 out of 15 runs flawlessly.
And OpenAI's GPT-5.6 Sol, the model that previously suffered a catastrophic collapse with a 3.1 on the blind Bemba track.
It catapults to an average score of 25.9 out of 26.
Near perfect, unassailable mastery.
This contrast yields the most crucial paradigm-shifting conclusion in the entire report.
By executing the blind test and the scaffolded test in parallel, the researchers successfully isolated the root cause of the failure.
They proved that this is not a capability problem, it is strictly an infrastructure problem.
That distinction is massive. Let's really break down the mechanical difference between those two problems.
If the AI's failure was rooted in a capability problem, it would indicate that the fundamental architecture of the neural network is simply too primitive to comprehend the abstract concept of syllable structures.
It would mean that even when you explicitly hand the AI the perfect alphabet chart, it lacks the cognitive machinery to parse the information.
It would look at the chart, become confused by the data, and still fail the test.
But the scaffolded results prove that isn't the case at all.
Yeah.
The models absolutely decimated the scaffolded test.
They possess the internal capability to utilize complex foundational systems. They know exactly how to operate the machinery.
The machinery just wasn't installed in the factory.
Exactly. The models failed the blind test entirely because the required foundational infrastructure, the explicit, machine-readable, digitized list of syllables, was simply absent from their training environments and their retrieval databases.
There's an incredibly revealing anecdote in the report that demonstrates this infrastructure deficit happening in real time. It revolves around the concept of tool use.
Yes. Modern frontier models, like Claude Opus 4.8, are equipped with autonomous tools.
Right. If they encounter a query they can't answer from their internal weights, they can execute web searches, browse databases, or even write and execute code to retrieve the missing information.
It's a crucial mechanism for grounding AI responses in factual reality rather than hallucination.
So when the researchers tasked Opus 4.8 with recovering the Mandarin pinyin inventory, the model analyzed the request, recognized it needed the exact standard, reached out to the internet, and actually attempted to use a Python package manager to pip install a linguistic library containing the comprehensive pinyin data.
Which is a remarkably sophisticated and rational strategy.
Oh, absolutely. The Mandarin pinyin system has been standardized by national bodies, exhaustively digitized, and integrated into countless open-source software libraries.
The digital infrastructure exists abundantly, so the AI simply executed a command to download it.
But then the researchers issued the exact same task for the Lavelle operating alphabet.
And the models engaged their tool use protocols. They reached out to the internet. They autonomously queried search engines, scraped linguistic databases, and parsed academic phonology papers.
And what did their search algorithms return?
Fragments. Disconnected shards of information.
They found partial grammatical descriptions buried in random academic PDFs. They found statistical evidence of the language being used.
But what they absolutely did not find was a single authoritative, comprehensive, machine-readable repository defining the Louvain operating alphabet.
The report notes that Claude actually explicitly communicated this failure in one of its responses.
Yes. It admitted that it was forced to try and manually reconstruct the Louvain inventory from scratch using piecemeal web data because it fundamentally could not retrieve a definitive, verified standard from anywhere on the internet.
This interaction exposes an unbreakable law of artificial intelligence retrieval systems.
A search engine, no matter how advanced, cannot retrieve a standard that humanity never bothered to build.
An autonomous AI agent cannot install a software package that no programmer ever wrote.
A massive million-token context window is entirely useless if the foundational document you need to feed into it simply does not exist in the digital realm.
The AI is reaching its hand into the dark, frantically feeling for the light switch, only to realize that humanity never actually wired the house.
But the report doesn't just diagnose the illness, it presents the intervention. It highlights the critical work being done by a specialized organization called Bantunomics.
Right, Bantunomics recognized this exact infrastructure deficit. They realized that waiting for an AI to magically infer these foundations was a dead end.
So they undertook the painstaking, grueling human work of explicitly curating, calibrating, and digitizing 459 version-maintained, full syllable inventories for these languages.
The technological significance of this effort just cannot be overstated.
Bantunomics is actively taking linguistic knowledge that was previously scattered, culturally implicit, or entirely undeclared in the digital space, and they are rigorously translating it into explicit, machine-readable infrastructure.
They are building the alphabet charts.
They are wiring the house.
So we're now armed with a clear picture. We have the precise measurement tool, the L26 Benchmark. We have the necessary digital infrastructure, the curated FSIs. What is the path forward? What is the explicit prescription for the massive AI laboratories engineering the next generation of frontier models?
The report concludes by outlining a rigorous, 7-phase research program specifically designed for AI laboratories.
It's a comprehensive roadmap to shift models from mere statistical mimicking to true foundational grounding.
It starts by forcing honesty. Phase 1 demands that labs establish a blind baseline.
Right. Run your multi-billion-dollar architecture on these operating alphabets without providing the explicit answer key and transparently record the exact magnitude of the failure. Don't hide the blind spots.
But Phase 2 dictates that you cannot just look at the final numerical score. You must aggressively classify the nature of the errors.
Because two different models might both score a disastrous 10 out of 26, but fail for fundamentally different architectural reasons.
Is your model's precision tanking because RLHF made it overconfident and prone to hallucination? Or is its recall failing because it structurally confuses native syllables with the phonology of a neighboring language?
The error analysis reveals what the neural network falsely believes the structure of the world is.
Phase 3 then introduces the scaffolded condition. You explicitly hand the model, the FSI, and mathematically prove that your architecture actually possesses the capability to utilize the standard once provided.
Phase 4 is where the heavy engineering begins.
Yeah.
Integration. You can't just paste the list into a chat prompt every time.
No, labs must integrate these FSIs deeply into the foundational architecture of the model itself.
Embedding them into pre-training regimens, fine-tuning protocols, or creating dedicated phonological representations in the tokenizer.
Phase 5 evaluates the real-world impact of that integration by measuring downstream effects.
Once the AI is structurally grounded in the true operating alphabet, does its generative text-to-speech engines stop sounding robotic and start producing natural cadences?
Does it permanently eliminate bizarre spelling hallucinations? Does it suddenly gain the ability to correctly recognize and translate exceptionally rare native syllables?
Phase 6 tests dynamic classification. Can the upgraded AI look at a massive, messy scrape of real-world internet text and accurately tag the data in real time?
Can it say, this specific string of text operates on native structure, but this string over here is clearly a borrowed foreign name?
And that leads to Phase 7, which represents the ultimate Hassabis-Einstein challenge for AGI development.
You take a frontier model, and you explicitly train it on hundreds of these fully calibrated, complete FSIs.
You don't just teach it the specific syllables, you teach it the abstract mathematical concept of discovering a closed linguistic foundation.
Then you select a brand new language, one it has never seen a standardized inventory for.
You deliberately withhold the FSI. You hide the answer key.
You feed the model only the raw, chaotic, noisy text evidence of that new language from the internet, and you instruct it. You now understand the mechanics of structural discovery, analyze the noise, find the edges, and explicitly define the operating alphabet.
If a neural network can successfully execute that task, it proves it hasn't just memorized a list of data points.
It proves it has synthesized a generalizable, reasoning-based method for extracting hidden truth from chaotic evidence.
Exactly. And if we zoom out to the macro level, we can clearly see why this matters far beyond the realm of linguistics.
Why should a theoretical physicist or a biochemist hunting for novel protein structures care whether an AI can successfully recover a syllable inventory in Bemba?
Because the abstract architectural structure of the problem is completely identical.
The underlying cognitive mechanism is the same.
It is the exact same reasoning mechanism. Whether a system is analyzing millions of linguistic syllables, sifting through chaotic telescope telemetry to identify the gravitational wobble of a new exoplanet, or analyzing vastly complex molecular folding patterns to design a cure for a disease.
The objective is always to move from noisy, chaotic, observed evidence to a hidden, underlying generative explanation.
To succeed at any of those tasks, the AI has to possess the ability to identify the core primitives.
It has to recognize and reject false patterns that look statistically probable but are structurally invalid.
It has to meticulously separate the genuine signal from the background contamination.
And most importantly, it has to possess the structural awareness to know when its internal model of the system is closed, bounded, and complete.
A truly useful scientific discovery engine cannot just rely on statistical probability to hallucinate a highly articulate, plausible-sounding hypothesis.
It must possess the architectural rigor to identify the correct hidden structure.
The L26 benchmark is profound because it provides a bounded, mathematically precise, perfectly measurable environment to test this exact capability today.
Before we trust in artificial intelligence to discover new, unseen laws of nature, we must first mathematically prove that it can discover the foundational rules of a human language it already claims to comprehend.
That brings this entire deep dive right back to you, sitting at the table with us. You might be wondering why the structural failure of an AI in a language you don't speak matters to your daily life.
Why should you care about this when you're just using a chatbot to summarize a meeting or write a line of Python?
You need to care because these frontier AI models are rapidly, aggressively becoming the foundational infrastructure of our global digital reality.
Within the next decade, these architectures are going to mediate how humanity communicates, how we acquire knowledge, and how we access vital information.
No artificial intelligence system should ever be trusted as a definitive master of multilingual capabilities or trusted with general scientific reasoning if its underlying architecture treats the English alphabet as an absolute, non-negotiable structural baseline, while treating the foundational infrastructure of the rest of the world as optional, secondary, or something it can just blindly guess at.
If failing to reliably identify A through Z is considered a fatal catastrophic engineering flaw for an AI, then failing to comprehend the foundational structures of other major human languages must be treated with the exact same level of scientific severity.
It fundamentally comes down to whether the technology truly comprehends the entire world, or if it merely comprehends the specific, heavily documented portions of the world that dominated the early internet.
Let's summarize the remarkable arc of this analysis. The L26 benchmark provides the exact, unforgiving mathematical measurement of the AI's current failure.
The meticulously curated full-syllable inventories, pioneered by organizations like Bantu, provide the explicit missing infrastructure required to bridge the gap.
And the Hassabis-Einstein thought experiment provides the ultimate philosophical challenge for the future of AGI, the necessary evolution from stochastic memory to structural discovery.
The data clearly shows that today's frontier models can operate the foundation if we explicitly hand it to them, but they do not yet possess the architectural reasoning to discover it on their own.
I want to leave you with one final, broader implication to process. As we have seen throughout this analysis, these massive AI models are ultimately pure reflections of our existing digital ecosystem.
They failed to discover an operating alphabet for these languages, quite simply because, digitally speaking, humanity had never built one for them to find.
The neural networks could not read a standardized manual that was never written.
The infrastructure simply wasn't there.
But acknowledging that fact forces us to confront a much more profound, unsettling question regarding the future of AGI.
If we look beyond language, beyond syllables and alphabetic characters,
What other critical foundational human systems are currently entirely missing from the explicit digital record? Think about the complex architecture of cultural norms, the unwritten, nuanced rules of human values, or our implicit ethical boundaries.
are we seriously expecting these massive trillion-dollar neural networks to simply figure out the architecture of human morality by statistically analyzing the incredibly messy, toxic, contradictory, unstructured corpus of the open internet?
Purely because we haven't taken the painstaking time to explicitly declare and encode those foundations for them.
If the most advanced supercomputers on Earth cannot mathematically infer a finite list of 480 syllables without an explicit curated guide, why do we assume they will naturally flawlessly infer the infinitely more complex hidden structure of human values?
If the manual isn't explicitly written, the machine cannot build the foundation. And right now, the explicit manual for a massive portion of what makes us human simply does not exist in their training data.
Thank you for sitting down with us and exploring the architecture of intelligence on this deep dive. The next time you watch an AI generate a flawless paragraph or instantly compile a complex piece of code, remember the blind spot. The machine might be generating brilliant text, but it still doesn't know how to build the alphabet. We will catch you next time.